All right, here we're looking at section 3.2. So we're in chapter 3 looking at section number 2. And here's our learning targets for today. First, we're going to draw and interpret scatter diagrams. And we've done some of this hopefully in the past, but now we're going to do some other things with it. We're going to look at some linear and nonlinear relations, and then we're going to find the line of best fit. And I'm also going to walk you how to use Desmos to find that as well, because we'll use that a bunch this year. So first we're going to draw our scatter diagrams. So in baseball, the on-base percentage for a team represents the percentage of time that the players safely reach base. The data given in this next table that I'm going to show you represents the number of runs scored, which is Y, and the on-base percentage for X during our baseball season. So first we have to draw our scatter plot, and then we need to draw my scatter diagram, okay? And then we're going to describe what happens based on our data. Okay, so here's the data that we're looking at, right? And they've gone ahead and put it in XY format for us with all of the different teams, our on-base percentage, our runs scored, and now we have to try and figure out what does this actually look like. So we go ahead and graph them. Okay, so my scatter diagram, I just plot them, and then we use, right? So here's what it looks like if we use something like Excel, and here's what our TI calculators look like. We can also use Desmos. Here's what our scatter plot looks like in Desmos, right? And we can see that it's a scatter plot because there's different points kind of everywhere. Okay, so that's kind of what our scatter plot looks like. So then I can look and see, based on this trend, it looks like as the on-base percentage increases, so do the runs scored, right? So I can follow the trend of my line, which is pretty cool. So now we're going to look at linear and nonlinear relations. Okay, so these ones all kind of make sense. So if your data, once you've put it in a scatter plot, if you can draw a line through it and it follows that line, then we're linear. These with curves are not linear data, and we'll look at them later on this year. Okay, so first we want to figure out, am I dealing with linear or nonlinear relationships? So this first one, I see, yep, it's all kind of going the same way, so that one is linear. This has got a curve, so it's not linear. Again, I see a curve, so it's not linear. And again, I see this kind of curve. So again, not linear. So I can just look at my data and kind of determine that as well. Okay. So now we're going to find our models for our linear data. Okay, so I want to use the data from table 6 from before that baseball point. So the first thing we're going to do is select 2 points and find an equation of the line. So here's where this gets tricky if we do it by hand, because based on my 2 points, I could have a very different line. So here's my scatter plot. So if I pick this point and this point as my 2 points, you'll see my line would go something like this. But if I choose this point and this point, I have a very different equation. Okay, so let's continue with our example. So we just picked 2 points. So we're going to pick these two, for example, and for this, it doesn't matter. We're going to get to the point where we use our graphing utilities in Desmos to get our exact answer. But for now, we're just picking some points, and we have to find the slope. And remember that slope is the difference in y over the difference in x. So I take my 688 minus 610 divided by 32.1 minus 30.6 to get my slope. Okay, so I find out that my slope is 52. And when we're writing these, we always want to write it, I generally like to write it in slope-intercept form, right? So y equals mx plus b. So that we just found our m. We found our slope. So we can also use point slope form to actually write the equation. We can actually use this as well, using our y and our x from up here to find our y-intercept and rewrite it. But sometimes when we're actually writing an equation, it's actually easier to use point slope form. So I just plug in the information I know. So I've got y minus y1 equals m times the quantity x minus x1. And this is the general form, point slope form of a line. So I plug in what I know. So I have my m, my slope of 52, and I'm going to pick one of the points. We just pick 30.6 and 610. It doesn't matter which point you pick, but those are your y1 and your x1. So we plug those in. We distribute my 52 into both of those, and then I'm going to add my 610 to both sides. So that's exactly what ended up here. So there's the model that represents what we were looking at. So we can also then draw our graph with that model. So this, you'll see I'm on exactly those 2 points. So you'll see that this may or may not best represent the data that we're looking at. Okay, depending on the 2 points you pick, you may not get the best results. So that's why we use graphing utilities to figure out the line of best fit, because we want the actual exact result. Okay, so we're going to use that same data that we've been looking at. We're going to find the line of best fit, and we're going to determine why it's the line of best fit. Then we can graph it and interpret. So let's go ahead and look at Desmos. Okay, so the first thing we want to do when we're using Desmos to find the line of best fit, and we can use this for any equation, is we first put our data in. And in order to do that, we open a new graph and we go over to our plus and add a table. That's how I entered all of this data. And this is the same data you'll see. So then to use Desmos to find this line of best fit, I go ahead and I type in my equation of a line. Right? So my general equation of a line is y equals mx plus b. Well, it's not real sure what I'm looking for here. So I have to be a little bit more specific. I need to tell it exactly what data to look at. So I want y1, whoops, and x1. Right? And I use x1 and y1 because that's the table that I have. I have x1 and I have y1. Well, and I know that this won't be exact because it was a scatter plot. So I can use this instead of an equals. Okay? And this little squiggle can be found above the tab key on your computer. Okay? So now we can look down at our data. We want to try and see what this all means. Okay? So when we're dealing with scatter plots and we're trying to determine the best kind of family of function to use, we always kind of look at our R values. The closer to 1 you are, the more exact it fits. So we always want to find our R value closest to 1. But then you'll see that this gives us our slope of 49.39, so about 49.4, and our B, our y-intercept of a negative 906.3. Okay, so now it gives us all of that and it draws it for us as well. So let's go back to this example. Okay, so there's our line of best fit. So I've graphed it. So I'm interpreting the slope. So when I interpret the slope, I can go back to what I'm looking at. So the slope would be 49.4. So that just tells me that for every 1 increase I have in my x, I have a 49.4 increase in my y. And if we look back at the data, right, we see, we can look here, that our x was the on-base percentage. So for every 1 increase in on-base percentage, the runs scored goes up by approximately 49. That's interpreting my data and the slope of my line. Okay, so now I can also use the line of best fit to predict the number of runs a team will score if their on-base percentage is 33.1. So that I can also use, I can use either my graph or I can use the equation, either one. So let's first look at what we did here. We're just going to follow along. Okay, so we see that they used the linear regression feature in your calculator, which there is a linear regression feature, and it will give you this model. Okay, we are then asked to figure out the on-base percentage, or how many runs when we have an on-base percentage of 33.1. Well, I know that x was my on-base percentage, so I could just plug in that 33.1 into my equation and simplify and solve. I can also use my Desmos to find that as well. Okay, so I can set, I'm going to go ahead and type my equation right below, just because so I can see it. So y equals 49.4x minus 906.3. Okay, and you'll see that my two lines are really close to each other, so that works out well. So now I can replace this x with my 33.1. So when I do that, Desmos actually acts as my calculator as well and gives me 728.84. So it helps me as well to come up with this final about 729 runs, which is what we got here as well, which is pretty neat. Okay, so you'll see this is just kind of what it looks like on your graphing calculator. If you want to walk through this with me, just come and find me. I have several of these on campus that we could play with and just check them out as well. So let's look back at our learning targets. First, we drew and interpreted scatter diagrams. We can draw these by hand. We can use Desmos. We should use Desmos a lot to help us with this. We looked at linear and nonlinear relations, and this will continue to come into play later on. And then we used a graphing utility to find the line of best fit. Just remember, when we're using Desmos to find that line of best fit, we want to use the squiggly instead of an equals, and we want to determine and tell x1 and y1 based on our table of data. Okay, so now that we've gone through this, go ahead and work on your homework for this section.